For those of you who are not familiar with what we're doing today, of course, we're having a smaller virtual event, but the advantage being that we can actually have a much larger audience, and we're up to almost 140 attendees, so it's already very successful from that point of view. We had planned a one-day event, so it's now virtual, and what we wanted to do was celebrate the agreement between ILL and our partners, so UGA and UGA, so Grenoble University, and HZB, Helmholtz Berlin, in our imaging activity at ILL. So the agreement we've put together between these major partners in our imaging activity is called NIMATERS, so that's Neutron Imaging for the Mechanics of Materials and Energy Research. And it's an activity that, if you like, rewards the partners for their critical input to this imaging activity, but also allows us to make developments that will feed back into the user program and support and develop the imaging activity at ILL. So this imaging activity is relatively new to us. It grew up a few years ago on an instrument called D50 with the Laboratoire 3SR from the university, which Chino was leading at the time. And the activity has gone from strength to strength. And this year it has become a public imaging instrument. We now call it NEXT. And it will continue to go from strength to strength, because in addition to NIMATERS that we're celebrating today, there is also a major instrument upgrade to ensure that we have a truly state-of-the-art facility at ILL in the years to come. So without further ado, we'll get on with the program, because our speakers and then our directors will say more to give you, the background and the really interesting aspects to this activity and the NIMATERS research activity. So as I say, we've got three what you might call, let's call them scientific and technical talks. So essentially almost the next hour and a half. So I'd like to, first of all, ask the panelists to turn off their cameras, and then we'll just have the speaker with his camera on. I can say his because we haven't done very well for gender balance today. And the first speaker is Alessandro Tengatini, who represents the university and the ILL, but let's say the university today, for symmetry with the other speakers. And Alessandro is going to tell us about cold neutron and X-ray imaging at ILL from D50, the initial instrument, to NEXT 2.0, the future instrument. So Nikolai, if you can hide turn off your camera as well, I'll turn off mine. And Alessandro, I'll come back on when after 18 minutes, and then you'll know how much time you've got left. I'll start to put you under pressure. So Alessandro, the floor is yours.
Hello, everybody. I hope you can all hear me. So today I have the challenging task of trying to tell you a bit about the story of imaging at ILL since about 5 years ago to projecting it towards the future as we hope to see it shortly. As you can tell from the rather long list of names, there have been a lot of people that have contributed to this instrument and in his relatively short history. And I'll try my best to try and portray a bit of what everybody did and all the work of all these wonderful people that I am today representing. So the story starts in 2015 in a collaboration between the Institut Laue Langevin and the Université Grenoble Alpes. We initially called the instrument the 50 Tomo because it lied on the 50 beam position. Tomography, of course, because it was a tomography instrument lying, in this case, behind another Rainbow's reflectometry instrument. And we shortly started nicknaming it NEXT, and we'll see in a second why NEXT. But let's talk about a bit the partner. Of course, all of us are quite familiar with the Institut Laue Langevin, so it's a source of neutrons, a reactor type source of neutrons, the most powerful in the world in its kind. And this allows the instrument to have a unique flux. Currently, the highest flux for a cold neutron imaging instrument. The other partner is the university, spearheaded specifically by these Laboratoire13, which was financially backed also by some industrial partners such as Total and EDF. For those of you who do not know the Laboratoire13, it's a laboratory that in the last 30 years has been having a very important activity on X-ray imaging, specifically on porous media, for a variety of geometry, for a variety of scale, from the almost engineering scale down to the nanoscale, using our own internal scanners, but also taking advantage of the synchrotron facility here in Grenoble, and tackling a broad range of problems. But there's always been a specific subset of problems that has always been trying to escape us, which is the one of fluids. Now, it might look small in the big picture or big scheme of things, but it is quite important if we think about water reservoirs, hydrocarbons, and so on and so forth. When I say that in X-rays this is not ideally tackled, well, it suffices to try and see an inhibition test, so just pushing water through a rock, and in X-rays it's hardly visible what's happening, whereas in neutrons the same exact process is perfectly visible, and thanks to the completely different contrast at the atomic scale. I don't want to repeat this slide. You probably have already seen it 100 times. They have different interaction, but what I'd like to stress here is how these two radiation types have highly complementary properties, which is a bit the idea behind the next instrument, which stands for neutron and X-ray tomograph. So the idea in 2015 was to build an instrument which would be capable of doing good, actually best possible, we could achieve neutron imaging as well as X-ray imaging at the same time, fully simultaneously. Now, before I describe a little bit this instrument, I'd like to remind a little bit the many people who have contributed to this wonderful instrument. On the UGA side, of course, Gino Vigiani, Edward Ando, Stephen Hall, Jacques Deroux, that's myself, but also in the ILL side, Jérôme Boucourt, Duncan Atkins, Charles Simon, and of course, Benjamin Giroud. So in its first year, we managed after about 8 months to build our first detector, our first initial tomograph, which in itself was not revolutionary in the approach, but it still allowed to do some very good science. One of the first problems we tackled, for example, was fire in buildings, specifically in concrete buildings. To try and follow this highly heterogeneous process, we needed to do, and very rapid process, we needed to do relatively quick tomographies at around 1 minute per tomography, while doing an operando test, by heating a concrete sample at about 500 degrees and acquiring a number of tomographies one after the other in quick succession. If you look at what this looks like, this is the water as it dries up in about an hour. Each one of these tomographies is 1 minute apart, which in turn allowed us to follow these the speed of the drying front for different types of concrete. And as you can see here in red, the temperature profile is identical, whereas the drying profile is quite different depending on the kind of concrete. Besides this improved understanding of the different processes that are induced by the micro scale properties, we also could, for the first time, verify an hypothesis that up until then had only just been supposed, which is the fact that ahead of the front there is an accumulation of moisture, a moisture clog, which eventually it creates a cork, which increases the pressure of the vapor, which eventually allows the concrete to spoil, so to explosively eject, which then exposes the reinforcement bar, which is what can cause the collapse of buildings. This was then reported in a number of publications. So this was one example of the very early works. But even this relatively simple first detector allowed us to break some world record. Specifically here, we can see the first published example of 1 second tomography, 1.5 seconds technically, of a waterfront within a soil, specifically within a lupine root. We were specifically interested into the effect that this lupine root had on the neighboring soil, on the so-called rhizosphere. And this is also an interesting example because it was one of the very first collaborations with HZB. So this was the first of a number of examples I'll try to highlight along this presentation to show how this collaboration between the university, the ILL, and HLB is a true collaboration that has been developing across the last 5 years. Another key feature, which we quite rapidly added to the instrument about 6 months after about the first tomographies, was the X-ray tomography system. For this one, a new member of the team joined us, which was Nicolas Noir from CNRS. His contribution was absolutely instrumental in getting this setup up and running. The setup itself it was designed to have compatible features with the neutron imaging, so similar field of view, comparable resolution, but most importantly to allow for a fully simultaneous X-ray and neutron acquisition. I mentioned before that these two radiations are highly complementary. Here is one key example, for example, for concrete once again. If you look on the right in the X-rays, it's relatively straightforward to identify the pores, but it is not very obvious how to distinguish aggregates from the cement paste. Conversely, in the neutron image, the aggregates and the pores are hardly distinguishable, but it's very easy to spot the cement paste. Additionally, thanks to the isotope sensitivity of the neutrons, it was possible to distinguish between the heavy water in which this concrete was cured and the normal water which was pushed through. So it is only thanks to the combination of these two techniques that it is possible to identify all the possible phases. And this was, for example, the focus of a number of work developing the maths and developing softwares behind that allow to use these features on the one hand to spatially register this radiation. This, for example, was the work of Stéphane Roux, Edward Ando, and many others I won't have time to mention. That also allows in turn to identify quite rigorously the different phases that compose this image, this 3D volume. Up until now, one could argue that other than the evolution of the water injected through, which is visible through the neutrons, the X-rays might have been just one initial tomography since the microstructure doesn't evolve. But there is a number of cases in which both the microstructure and for example, the hydraulic properties evolve. That is, for example, the case of Karlov, Oxfordia, and clay rock. This rock, which is particularly important in France because it's one of the key candidates for storing nuclear wastes. For long-term storage, and when we put this clay rock in contact with water, this is what happens. We see the X-rays on the right and the neutrons on the left, and as you can tell, there's quite a violent reaction. Thankfully, I want to reassure you the side conditions are quite different, so it is not quite possible for the rock to react quite as violently. But it is obvious that both the microstructure and the fluid properties evolve. And the X-rays are ideal to catch this tiny evolution of fractures and volumetric expansion and water injection. This was a first set of tomographies and radiographies, mostly in 3D. We did then following campaigns in which we fully exploited the 3D natures of the true radiations. But what I'd like to highlight here is that once again, I'm not gonna have time of showing case by case what kind of analysis can be done behind all this, but of course the final aim is not just to acquire beautiful images, but rather to quantify processes. So for example, thanks to the X-ray imaging, it is possible to measure the displacement field, which you see here on the right, and therefore estimate an incremental strain field, which allows us to dissociate that which is volumetric dilation and generally strain from what is the actual injection of water, which is what has been done here on the plot on the left. Once we've achieved this simultaneous X-ray and neutron imaging, we also tried to push a little bit the resolution as far as we could. This was based on an approach initially proposed by HLB a few years before, and after a number of iterations, we managed to push the resolution to below 3-4 microns, let's say, which we can see here on the bottom left. We can see the individual spokes of one of the classic target objects in X-ray imaging, which is about 4 microns in size. This, of course, is very interesting for a number of applications. I'm going to mention another case of a collaboration with HZB, which is batteries. We can see here on the X-ray side, we have wonderful information about the evolving microstructure, so the evolution of the sponge inside the battery, as it is cycled through charge and discharge cycles. But the X-rays cannot provide information about the electrochemistry, so specifically about the lithium, which can only be captured thanks to the unique attenuation of lithium to neutrons, which we see here on the right. Is once again only through the combination of these two techniques, and only thanks to the high resolution imaging made available by the developments, that it is possible to capture the full complexity of this battery. This, for example, was the focus of one recent paper on Nature Communications. And if you've never seen it, this is what the inside of a battery looks like. Each one of these frames is actually a slice of a 3D tomography of a roughly half-an-hour tomography. And what you've just been seeing is the lithium moving away from the electrolyte and into the cathode as it gets discharged over the course of about 8 hours. I'm not gonna, I haven't had time to show you all the very many scientific applications that the instrument has made possible. I've tried to highlight, of course, the ones which were on one hand very much the core interest of Laboratoire Alpes, but also the very important collaboration with HSP. But there's many others, of course. I'll be ever so pleased to discuss about any of them. This good fortune of the instrument is also reflected by an increasing demand. This is, for example, the map of distribution of the beam time request of the last cycle, and the topic distribution. I've made a fair number of examples on fluid flow, environmental applications, batteries, but there's also, of course, fuel cells, archaeology, additive manufacturing, bolts, biofilms, and so on and so forth. There's an increasing number, as I was mentioning, of requests, which unfortunately corresponds to an increasing overbook factor, and an increasing number of publications, which are finally managing to get momentum. To get you a bit of an idea of how all these components fit together, what the instrument in a broader sense looks like, this is the keystone of the instrument. This is the granite table which holds the whole setup. In red here we see the X-ray source, and opposite to it the X-ray detector, the flat panel. 90 degrees from it, the neutrons come from the left and are detected with the detectors on the right. And there is a rotation stage here, which is hollow, which is one of the key elements of this tomograph, as it allows for this operando test, or all these set of tomographies that are repeated over time as the samples are mechanically, thermally, chemically loaded. This tomograph is fit within, of course, a radioprotective bunker, which we see here on the left. One of the key limitations we have today is that we are at a fixed position from the pinhole, which limits our possibilities in terms of neutron collimation, and also the relatively small space is only about 3 by 4 meters, which has been enough for all tests. But of course, it would be wonderful to have a bit more space for these inoperando tests. If we had to list all the limitations of this first iteration, beside these geometrical constraints, there's the fact that up until now we only explored polychromatic beam. There are no polarization options, and there is no possibility, for example, of grating interferometry. So all these advanced contrast options. It is having these limitations in mind that in 2018, a team led by Edward Ando and the D50 team, and sustained by a large number of people in our community from UGA, HZB, but also the Lund University, LLB, LMT Kashan, PSI, ESRF, has managed to obtain fundings within the Endurance 2 scheme, within the upgrade scheme of the ILL, to do a complete refurbishment of an upgrade of this instrument. Before I try to tell you all about what we dream to have in the next couple of years, I would like to remind you with the key partner in this collaboration, of course, ILL and UGA, but also HZB, which is going to be contributing with a number of equipment elements, but also with a broad know-how that have been developing in the last 20 years. These three institutions collaborate a little bit through this international mixed unit, which we named NI Matters. in a very concrete way. On the one hand, the personnel, resources, and his own dedicated beam time, but also through PhD thesis, also through a chair between UJ and ILL, yearly budget for internal project, and even his own scientific council, which will help direct the scientific direction of this body with the very important help of Stefan Roux, Stephen Hall, and Robin Warchek. Beside this element, in the view of this upgrade, there's been also an expansion of the team working around the instrument. In 2019, we were joined by Lucas Helfen, who will present just after me. Calvin Buckley joined us, but also the essential contribution from our wonderful technical team, from Emilio Ruiz, which has been wonderful, but also, of course, Baptista Modrus, Luc, Didier, and all the people that I will not have time to mention, which have been giving great help in the design of the new instrument. But last but definitely not least, all the huge help from the HZB team. So of course Ingo Manke, Nikolai Kagilov, Andre Hilger, and Tobias Arlt, which have been contributing in the scientific direction of this new instrument. Let's have a quick look about what we dream to build in the next couple of years. As you can tell, there's a lot more space for the tomography. It is possible to adjust the position of the tomograph itself along the line, along the neutron beam line. There's a dedicated user space, but the main difference, the main improvement are going to be, of course, in the way we can affect the beam itself. We're going to be able to do monochromation through velocity selector, double crystal monochromator, but also do polarizations options, grating interferometry. And even in the tomograph itself, we're going to expand the X-ray possibilities. We're going to add, we're going to push further the resolution, and even add laminography setups, and all these things are going to be detailed in much more richness by my colleague Lucas after me, and all the advantage, the interest of all these advanced options will be presented by Nikolai after him. So to summarize a bit, the dream of the new instrument is to expand the portfolio and increase the possibilities offered to the user community. To give you, this was a bit what I've been showing you thus far has been the artist rendition of what we want, but the design is well on its way. This is what the actual bunker looks like. As you can tell, there is a secondary station, which I haven't mentioned, so they will be able to extract part of the beam for a monochromatic station, which will be focused in these advanced contrast options. The bunker is much broader than before. It has a concrete part, which for its extraction, for insertion of large, bulky samples. There's a lead part, and even in the collimation, the design is well on its way. We managed to put the vast majority of the components I mentioned within the setup, and we are currently starting to focus on the tomograph itself. To give you a bit an idea of the timeline, if you're interested to come see us, we will have 3 more cycles in 2021. In the meanwhile, we'll of course complete the design and start the fabrication of the components. There will be a long shutdown of about 12 to 13 months starting from August 2021, in which we will install these components. Of course, we will do the commissioning, and eventually starting from August, September 2022, we'll be fully open to the public. I'd like to conclude just with this rather busy last slide, in which I try to summarize all the contributions of all these people that helped made this instrument possible. That some of them are at the beginning, and more adding them as time passed. As you can tell, there have been a number of technological developments along the years that have made possible an increasing number of science, and in 2022 we'll be able to further expand the portfolio in this new version of the instrument, also very much helped and supported by this international mixed unit NII matters.
Thank you, Alessandro. Perfectly on time, so that's already a very good start. That was a wonderful talk. Thank you very much. There are a couple of questions for you. There's a few coming in. So Alan Hewitt, I won't give the microphone over today since we haven't got that much time. So what's the field of view if you have a 3-micron resolution?
It's a few millimeters, of course. Normally, the number of pixels is about 2,000 to 4,000 So of course, for 3 microns is 3 microns times that. The field of view was 170 by 170. We are talking about an 80 micron resolution in that context. In the upgraded instrument, we will allow for much broader fields of view, up to about 30 centimeters. And we will, of course, try to push resolution. But of course, large fields of view and resolution, they don't go along together. They need to be they're separate setups.
Okay, and Alan's very interested in detectors, so he wants to know what scintillator you use.
A broad range from lithium fluoride to gadolinium-based to a series of gadolinium-based scintillator. But we are even working in collaboration with Munich and with the US on boron-based on development of boron-based scintillators.
Okay, the next question from Brent Heuser is the variable position of the station is to allow different L/D for high versus low resolution modes, or are there other reasons?
Indeed, there's a field of view effect. The further away we are, the more we allow the space to the field of view to increase. The closer we are, the more we can push the LOVD, the flux in the right conditions. But there's also a matter of gradient of wavelength. So when we monochromate, there's typically spatial gradients of the wavelength, and we can to some extent play with how important it is depending on the distance from the beginning of the casemate.
Okay, Paul McMillan asks, is there a possibility for studying dynamics with contrast, or is that out of reality?
I'm not sure what is meant in this context with contrast. Dynamics-wise, we've been able to push very much the maximum speed. We're talking about 1 second tomography, which means also the radiographies can be done in a fraction of a second, really, up to 100 hertz easily, even 1,000 hertz in some particular conditions.
Okay, I'm being a little bit selective now. There's lots of questions coming in, so let me go to another question, and well, actually one I can ask, and that will give Alessandro a break for a moment. The instrument works also in reflectivity mode with rainbows. Won't there be any upgrades on the instrument for that mode? And thanks for a very nice presentation. So thank you, Lucine, for that nice remark. The D50 was a sort of hybrid instrument with several uses. It's now dedicated to imaging. One of the great things done there was to test this new reflectivity option called rainbows, and we are planning to install that on our reflectometers D17 and Figaro in due course. Okay, let me another one that I can answer. So we've got Ranji Ramadan. Is it possible for international research community outside Europe to take benefit from this partnership and facilities? Ranji and everybody, you should know that we have a user program which is for 80% of our beam time, which is essentially for our scientific members. That is and associates. These are the people who pay for the ILL and make the whole activity possible. We have a small amount of beam time called director's discretionary time that we can award for any excellent science that we want to do. So that is a route for anybody to come in and use our facilities, not just for imaging, but for the imaging. Alessandro and colleagues, they set up a nice open call to use the beam time that they had on D50, and that will continue with NEMATers in the future. So there will be an opportunity there, and there aren't the same restrictions on that beam time that there are on ILL beam time. Let me find another one or two more questions. What about the dimension of a steel sample that can be studied? I think that's the question.
It depends on the resolution needed and all that. The field of view is going to be about 30. In principle, for elongated samples, as a steel beam could be, there shouldn't be any problem. One can do a helicoidal or a stacked scan. the width is limited essentially by, let's say, a couple of times the field of view. In terms of thickness, well, it depends a bit of the shape of the object, still, and the nature of the object. Steel specifically is not too opaque to neutrons, so I would say there's little trouble in that sense. Weight-wise, the table is designed for a few hundred kilos, so I don't see the problem in that.
Okay, and I think a last question, which it'll have a short answer, is great talk. So this is from Jeffrey Warren. Thank you, Jeffrey, for that. Do you have a plant growth chamber on site for maintaining plants during beam time?
Yes, actually we do. It was a wonderful gift from our colleague in Potsdam, from Christian Tötzke and Sasha Oswald. So we do, and it's a really nice one.
Okay, so I'd like to stop there with questions. So here's my applause for Alessandro, and I'm applauding on behalf of everybody. Thank you very much. If Lucas, if you could share your screen now. So the next talk is by Lucas Helfen, who is, as Alessandro said, the ILL instrument scientist, working with Alessandro on the next instrument, and he's going to tell us about high-resolution imaging of extended objects using neutron laminography and microscopy. And just before Lucas starts, again, we'll all hide our cameras. And for those of you to ask questions, use the Q&A, as most of you have did. Some of you used the chat, but it's a bit easier to manage if you use the Q&A. So thank you for that. And Lucas, the floor is yours, and I'll come back after 18 minutes.
Yes, thank you, Mark. After this nice presentation from my colleague Alessandro, I wanted to speak also on behalf of the next team. So I put here the core next team, but of course I could have put many more people. At the moment we have the situation up to now. The next instrument was built by the UGA and the ILL together. So as Mark has pointed out, it will go into public operation, or it has been already assigned to public operation since 2 cycles. And so now it is to HZB to join us here. And we had already a number of nice experiments together. So that's a nice way of officializing these collaborations. So, and I want to go ahead here with my talk about the high resolution imaging of extended object using neutron laminography and microscopy. So as already pointed out, we have the different probes at NEXT. We have the X-rays and we have neutrons. And in many scientific applications, it's essential to get these complementary information about the sample due to interaction mechanisms which are different. And but in some applications also very a feature nice to have. And so we are using these probes, X-rays and neutrons, in order to do radiographic projection imaging of the samples. And so I want to give more an overview here of what's possible with tomographic methods, so 3D imaging and section imaging, using computed tomography, a standard method right now, and using laminography. So after that, I would like to go also explain a little bit what options do we have for other imaging geometries, because for the X-rays we are using, for the X-rays we are using the divergent beam geometry, so a conical beam, which allows us to obtain geometrical magnification. And with the neutrons, we are using the parallel beam geometry, where we need a strict collimation in order to preserve the spatial resolution. So I want to go a little bit into what other options do we have, for instance, focused beam scanning or projection microscopy, or also going towards lens-based imaging. So sorry again. The key questions, what we want to address here is how to realize and maintain high spatial resolutions for extended samples or samples which are in spatially extended sample environments. So I go quickly into the difference between tomography and laminography. Tomography is well established for very different probes, so ranging from X-rays to neutrons to electron tomography. So usually you have the rotation axis perpendicular to the transmitted beam direction in transmission imaging. And so you're acquiring with a 2D detector system a number of projection images under different rotation angles of the sample. And for a long object, it's quite easy to image the sample here. So it is a situation where you can individually image in the parallel beam geometry a small portion of the sample. Do that at different heights here along the sample, and then stitch the resulting 3D volumes together. What's also easy to do here is if the sample is not here as indicated at infinity, but closer and is laterally extended, sorry, the source is close and extended, then you need to go close in order to preserve the spatial resolution. Otherwise, you will have blurring of the images. And so this is where we need the collimation stage here. So it's easy in this geometry to preserve the collimation in order by going close with the detector to the sample. In cone beam tomography, it's a bit different. So what we use with the X-rays, that we have a divergent beam. And so we need to use a certain distance between the sample and the detector in order to get a magnification effect. So we have a macroscopic pixel size here on the 2D detection system. And due to the divergence of the beam, we can only reconstruct faithfully the strict center of the sample here on the on this section, which is perpendicular to the rotation axis and on the central beam direction. So we have equipped recently our instrument with a Z stage in order to perform helical scanning. So we can actually, by using the same helical scan geometry, reconstruct a larger portion faithfully of the sample. Going back to, so this is to fulfill the Tuohy-Smith data sufficiency conditions. If we use now, instead of the long sample or a cylindrical sample, if we use a flat specimen, we get to the problem that we need a minimum distance between the detector system, here the scintillator, and the rotation axis in order to be able to turn the sample. And also for some orientations, when the sample is aligned parallel to the beam direction, then you might have attenuation, lots of attenuation in the sample, and also no reliable projection data anymore acquired by the 2D detection system. For this reason, there is laminography techniques being developed so that you avoid actually these projection directions along the sample dimension. And what you do is, for instance, in a parallel beam geometry, you incline the rotation axis with respect to this theta angle, with respect to the transited beam direction. And then you can go much closer again with the detector towards the specimen. And you avoid these unreliable projection data. So here to summarize, ideal conditions are for tomography where you can approach the detector and you have a stick-like or a compact sample. Then you can acquire faithful data, but as soon as you go with a laterally extended sample and you have attenuating samples, then you get to a situation where you cut out wedges out of the Fourier domain of the specimen, and this then later leads to artifacts. Here in laminography, we get a similar situation. So one projection direction samples this plane here in the Fourier domain. So when we turn the sample and we fill the Fourier domain, we see then that we get these missing cones along the rotation axis, which are missing. But we see when we look at the comparison under simulative experimental conditions, we see that this is much better because we cut out less information from the Fourier domain. So this is here shown by this example of a wire bonded integrated circuit, where we see these wire bonds here. It's gold wires going to a substrate which has a couple metallizations. And we see that this is quite nicely reproduced in laminography, but very poorly. All the wires which are perpendicular to the rotation axis are vanishing and have very low contrast in the tomography, in the limited angle tomography example. So laminography is well adapted to flat objects, microsystem devices, flat artwork, plant leaves and roots, sheet materials, composite panels, for instance. And we did already some feasibility experiments that have been performed much before at Antares. I go only here quickly, and I show you what you can do here. For instance, this is a concrete exposed to a chloride solution, and what we see, we can nicely reconstruct the specimen and distinguish the cement matrix from the aggregates and the pores here in white. For interconnection technology, we see very different contrast. So we see all what is plastic and what is electrolyte, what is separators inside the components, and not so much the interconnects themselves. So we have now implemented that also at ILL. We did first laminography user experiments in September 2020. In collaboration with the main proposers was Christian Tötzke and Sarah Beresville. So here we are looking at a soil container where there are some complementary measurements done with fluorescence imaging with some foils which are sensitive to pH. Sorry, that is too early. To pH, U2 and CO2. And so these measure then the different heterogeneities of these gases and pH in the rhizosphere. And so what we do is we put the sample here on the rotation stage, which is inclined here, and acquire the projection images here with the detector system. So we can actually reconstruct that. So we have shown that here. So here is the rhizosphere, the roots which are going into the soil, and which can be nicely distinguished along with other hydrogen-containing materials. And we can even see the foils here, as I will show you here quickly on the back side. So here we see the foil, which is for the complementary fluorescence measurements. So here 2 slices through the volumes, and what we see is when we have an initial water content of 12.3 volume percent, and later on a dried sample with 8.5 volume percent water. So the plant has, let's say, extracted the water and used it up. And so what we see here is that first, the matrix is less absorbing, less attenuating in the drier sample, and especially the roots show much less attenuation. So because of the water content, which is much lower. So there we can go further on and explore that these preliminary data here, which we are looking forward to do, let's say, until the end of this year. So to summarize laminography versus tomography, we have in tomography these long extended samples which can be nicely imaged up to a certain spatial resolution limit in the Fourier domain. And in laminography, we get these missing cones. In tomography, you would also get, for lateral extended specimens, flat specimens, you would also get missing wedges, which makes then reconstruction more difficult. What we want to do now is to go with neutron laminography towards using really the high spatial resolution which we can obtain at ILL by inclining the detection plane parallel to the sample surface or perpendicular to the rotation axis, so that we get a closer distances, so we are not suffering as much from the collimation, and for the limited collimation, and that we can that of course goes at the expense of the usable beam height. But we are looking forward to that, and want to incorporate the detector tilt in our future instrument, and also adapt, of course, the necessary reconstruction algorithm. So for the imaging geometries, as I've pointed out, for the X-rays we are using this conical beam geometry. For the neutrons, we are using the parallel beam geometry. And it would be actually be quite nice to use also neutron magnifying schemes. But of course, we need to take care about the blurring induced by the finite source size. So we can consider two cases here. So here we have the object, and then there's a per-number blurring here on the detection plane. We can consider two cases where we have first the parallel beam geometry, where this distance here, L, capital L, is long. So there we need a good correlation. And we can distinguish the projection geometry case where this L is much smaller than the calligraphic L. So there we can get a high spatial, high magnification, but we are limited in the end by the source size itself in the imaging process. So why we want to go for high resolution imaging is that we our current highest resolution scintillation screens are somehow limited in spatial resolution. If you look, what is the conversion electron which is produced? What is the maximum path length and penetration depth? Sorry, that you may achieve is in the order of 5 to 6, or for the lower energies, 1.2 micrometers. So we see that there will be somewhere probably a limit which we will reach for the spatial resolution. And this is why we already want to get towards a magnification during the neutron imaging. So there are different approaches that we can go for. First is do a probe forming. So we are imaging actually the extended source onto the sample plane, which is here the image of the source. Closely related to that is the projection microscopy approach, that we use now the sample behind the probe or behind the focus spot, the secondary source, in order to get to image then, like in cone beam tomography, our specimen. But these two approaches have the problem that we need to have a very short focal length in order to reach these high magnifications, or to use a small source size, so of course, which is not useful for neutrons. So for the neutrons, we want to preserve this we want to preserve the polychromaticity of the sample. So these these short focal lengths are not well feasible for reflective optics, which we would like to favor. So then we have the lens-based imaging approach, where we have behind the sample a lens which images towards the detection plane. And here is also the challenge to preserve the energy bandwidth, and we want to have grazing incident reflective optics. So there has already been work performed by NASA and NIST. So Dan Hassey, for instance, using Volta-type mirrors. So these are axisymmetric mirrors which can be nested. And they have demonstrated that there's 50 micrometer spatial resolution feasible. Of course, this is something that has been done a few years ago. So perhaps now with new manufacturing technologies, one could go further. And the good thing is also that you can use in a M equals 1, so no magnification approach with two focal lengths of these parabolic minnows which are equal. You can achieve a flux gain in the order of 100 in order to use the divergent neutrons coming from the guide or from the source. So as I said, this fabrications is very demanding. So you go normally from a forming process on a mandrel of an aluminium mandrel that you are producing. You need to go for achieving 1 micrometer spatial resolution that has been shown by simulations. We need something like slope errors of 1 microrad and micro roughnesses of the mandrel of around 4 angstrom RMS values. And so that it's a forming process that you deposit the nickel onto this mandrel and then get it off by a temperature gradient. These optics are also used in space applications. So here, volta-type optics here for the X-ray telescopes like Chandra or like XMM. And you see the advantages that we have nested mirror shells, which can increase the collection efficiency and the compactness. There's also alternative approaches with planar substrates. So these advanced Kirkpatrick-Bayes optics, where you have 2 perpendicular reflections, hyperbolic and elliptical pairs, in order to do imaging of the sample on the detection plane. Here, you could use multi-layer supermirrors coatings in order to increase DNA and collection efficiency. And so these are the critical points. So also thermal expansion, gravity, the optics deformation. We get a neutron drift due to gravity. So we need to do FEM and ray tracing simulations to compare the different options that we have. So as an outlook, I would like to conclude that we want to use these complementary information about the samples that neutron and X-ray probes allow us to use. We want to use different tomographic and 3D imaging approaches, computed tomography and laminography. Laminography, I would say, is en route. Tomography is at next already since a few years available, so that's not our main focus. And then we want to explore the different imaging geometries. Full field parallel imaging between needs is our main objective for next. And then we want also to go for focus beam, looking into focus beam scanning. That is lens partners at FIM2 who are looking into that. And we want to have a look at lens-based imaging in order to get rid of the collimation needs that we are facing. So that needs to be done in simulations, ray tracing, check feasibility and requirements. What is possible and what is necessary. That's of course an enormous technological challenge that we are facing here, and that will be tackled via an interfacility developments. So we have in next we have a PA which is dealing with that. So especially these optics developments. So we are looking towards a collaboration here. Because it's also enormous costs that we are facing probably, and so with these tools, then we want to develop the different science cases that we have. So geometrials, there's a core know-how or key mission of the 3SR at the UGA. We have energy-related research. That's a key HSB key mission. We have life sciences where new ways are opening up. And we want also to address, of course, cultural heritage and many other fields of in science where imaging is very useful. Thank you very much for your attention. And,
thank you, Lucas. Thank you very much. That was a very, very nice talk. So since Lucas has mentioned the other facilities through LENS and these developments that would be done on a collaborative basis, I'd just like to take this opportunity to thank the other European facilities like PSI, ISIS, Berlin, of course, Munich, and DSS, because everybody, and in addition NIST in the US, because the experts from those facilities came together in our project review panel and really, gave their expert input and helped us to define the best possible project to upgrade next. So thanks to them. So there's a couple of questions here. Brent Hauser again. Do you calibrate the absolute water content in laminography or tomography?
So far, we are. So I think Alessandro has already done experiments in that. Perhaps he can comment on that later. But here for these experiments, which I've shown you, we did not do that so far.
Okay. Alan Hewitt says, with or without neutron lenses, it's still an experimental technique. What resolution have you seen in real samples and at what exposure time? So resolution in real samples and what exposure time?
I have to confess that I've said myself, I have not done any experiments yet on that. I would go more to the first the simulation approach, but I know from people who have worked already with it that you can expect at the moment spatial resolutions as stated here in the order of 50 micrometers, which is of course not comparable to what we get with the collimated beam approach. The main advantage I would say is that you would be able to do local imaging either of samples in their environments, sample environments, or in that you do just local measurements with a high spatial resolution, so that you can in fact be much further away with the optic from the sample than you would be able to do that with a collimated beam in the detector.
Okay, thank you, Lucas. So one more question, Ken Anderson from SNS, I think. So if it's the same, the Ken Anderson I know well. So do you have sufficient space to extend the instrument in order to fully benefit from future microscopy developments?
We are having now something like 5 meters in the main hatch, and so I think it's of course difficult to say, but I would think that we need to go for compact optics, and with such compact optics you would probably not need a very large distance. There are also then other problems like gravity comes into effect. So if you're working with polychromatic radiation, if you go to large distances, then you probably need to compensate for these gravity drifts of the neutrons.
Okay, and I think we can always move other instruments if more space is needed, but that's that can be challenging.
Let's discuss that with WASP perhaps before.
Yes. So I think we'll stop there. So thank you, Lucas. I'll applaud on everybody's behalf, me and Chino and myself. That was great. So we move on now to the third talk, and that's Nikolai Kardylov from HZB. And Nikolai is going to tell us about advanced neutron imaging using different contrast options. So the floor is yours, Nikolai, and I'll come back in 18 minutes.
Okay, I'll try to keep it. So let me move to this one. So do you see the screen? So do you hear me? Okay, so I should, let me see. Wait a bit. So this one and this one. So do you see it now or?
Not yet.
Okay. Okay. I see. I should confirm it. Okay.
We can see your desktop now.
Yes.
Really clean. If you compare it to mine, it's a wonderful desktop.
I prepared it already. So good. So now you see. I think you see the my desktop, right?
Yeah. Okay. Go for it. Thank you.
Okay. So thank you very much for giving me the chance to present the work at HZB and also our contribution to this research unit. So I'm very impressed because I saw that we have more than 200 participants And I think we beat all the world records or whatever, all the records of interest in neutron imaging event up to now, because the world conferences which we have have about 120, 150 participants. And it's quite pity that ILL took so long time to go in neutron imaging topics and to build a neutron imaging instrument, because you see that the interest is really very high. So I'll try not to disappoint you with my talk. So 18 minutes is quite sporty, but okay, let's see. So we saw very nice talks from our colleagues from UGA and also from ILL, presenting the project at the neutron imaging projects and the new next instrument at ILL. So in my talk, I'll give more overview about the advanced neutron imaging, which was actually developed also here at HZB. Over the 15 years of operation of neutron imaging instrument at the BER-2 research reactor. So here you see a very nice location at the HZB campus, Lisa Meitner campus at Berlin-Wannsee. And actually at 20 kilometers away from here, we have a second campus where our large-scale facilities are located. So here at Berlin-Wannsee, we have the BER-2 reactor, and 20 kilometers away, we have actually the BESI-2 synchrotron ring. So actually, up to last year, we could say that we can benefit on the two large-scale research facilities of using neutrons and synchrotron radiation for our research. But the research reactor was shut down last year, so we gave up on neutron activities, and now we should continue our research with neutrons as users at our other facilities. So it is really quite sad to see how the research reactor is shut down. But actually, we were well prepared for this because our management spent a lot of efforts to discuss the situation with researchers individually. So for everybody of us, the best solution was taken. So you see some happy scientists at the final day of the shutdown of the reactor. And for us, actually, we got the chance to participate or to continue with the neutron research and participate in this nice joint research activity together with the colleagues from UGA and ILL. So our contribution will be to transfer knowledge and know-how and also components from the neutron imaging instrument CONRAD 2 to ILL, to the new imaging project at ILL, and also be able to transfer all the advanced neutron imaging capabilities from this instrument. So itself, actually our imaging project started in 2003 with the design and construction of the CONRAD instrument. CONRAD stays for cold neutron radiography at that time. And in 2005, we were ready and started after commissioning of the instrument with the user operation. So you can see here a team of young researchers at that time. So it's Nikolai Kachelov, Marco Strobel, Ingo Manke, and Andre Hilger. So under the guidance of the head of the Institute of Applied Materials, Professor Banhart, and the external advisor, from the University of Applied Science, Professor Treimer, we started actually the research program at the instrument in order to optimize its performance. So at that time, it was quite new to have imaging instrument which is placed at the end of curved neutron guide using the cold source of the reactor. And we spent a lot of efforts to optimize the performance of this instrument. So actually, it was clear that we cannot compete facilities or instruments which are placed or which are using high flux reactors like the FRM2 in Munich or potentially imaging instrument at ILL. So that's why we understood that speed and flux will be not our strength. And we focused more on advanced methods where not only absorption contrast is used for imaging. So the first results came about 3 years from the first start or for the commissioning of the instrument. And the first highlight was the magnetic imaging, where we succeeded to convert precession angle of the spin of the neutron in the magnetic field to contrast. And this was well recognized from the scientific community. So we got the chance to publish in Nature Physics and even to get the cover page of the journal. So after that, about 2 years after that, together with the help of the colleagues from PSI, we were able to install grating interferometry at the Conrad instrument and succeeded to perform the first tomography of using the grating interferometry, where actually the domain walls in iron silicon single crystal have been visualized in 3D. So we spent also some efforts on high resolution, and we transferred some solution for high resolution detector from our colleagues from the synchrotron beam line at BESI, and used this actually at the Conrad facility, where we in 2012 we achieved a resolution better than 10 micrometers. So in 2012, after a revision of our scientific program and the good results, we got the chance actually for upgrade of the facility, where we succeeded to get more flux due to the new neutron guide system installed at the reactor and the new cold source, and also get more space and how to say beam path distance for our instrument. So at the end, we had actually a quite good instrument with a lot of possibilities and scientific activity at it. So the most interesting thing is that it's placed on curved neutron guide and using the cold source of the reactor. And due to the curved guide, actually we got a very pure cold spectrum, as you see here. And this cold spectrum is very similar to the spectrum which we have at D50 beam line at ILL, where the new imaging instrument should be built. So this gives us the chance actually to contribute directly to the new imaging project at ILL and to transfer all the components as they are to this beam line and use them almost without modifications. So the strength of our beam line was the cold neutron beam in combination with some instrumentation, which gave us the chance to use advanced neutron imaging. So what means advanced neutron imaging? This is actually imaging which is complementary to conventional imaging, where absorption contrast imaging is used, where we have some moderate spatial and temporal resolution and single mode of imaging. In the advanced imaging, we actually are using some different kind of contrast. It could be diffraction, phase, or magnetic contrast. We are aiming for high spatial and temporal resolution, and here we are trying to apply multi-mode imaging, for example, combination of X-rays and neutrons. So here are some highlights from the recent years or from the recent time related to this advanced imaging applied on battery research. So we have plants physiology, so some fundamental research of visualizing magnetic fields and engineering materials. So in order to get these highlights, actually, we worked quite hard to implement different new or innovative methods for imaging. So here you can see the high resolution in combination with the dual mode imaging, the high-speed tomography, the tensoromagnetic tomography, and also the energy selective neutron tomography. So at the sum of the examples, you see the logo of D matters already, because for these applications and for these actually examples, we worked together with the colleagues from UGA and ALL, and part of the experiments were performed at ALL. So this means that the cooperation is already alive and we are working together. So here I'll focus at all these method developments and show the capabilities of them with some examples, starting with the high resolution imaging. So for this, we used, as I told you, a design which we overtook from the colleagues at Bessie. So this is the infinite correct optics, where two lens systems are facing each other. So due to the ratio of the focal length of the two lenses, we can have optical magnification or even demagnification or having zoom out. So then actually we have very flexible system where by changing of lenses, we can change the pixel size of the detector by using of this optical magnification or demagnification. And in this way, we change also the field of view. So the best resolution which we achieved was about better than 5 micrometers recently with colleagues from the New Matters research unit. And for this, we used a camera with 5,000 by 5,000 pixels. So this means that, and pixel size of about 1 micrometer. So the field of view was about 5 millimeters. This is just going back to the question of Alan. So the scintillator was gadolinium-based scintillator which we got in cooperation from the colleagues from ESRF. So in general, this high resolution is quite impressive, but it is much more impressive if we can combine this with X-rays. And this is actually the big advantage of the new instrument, which will be set up at ILL, that we can perform simultaneously tomography of samples using the same spatial and time resolution. So implementing the high resolution detector, taking images in few seconds, then we can perform the measurement simultaneously. So here is the first example of this, investigating of lithium battery based on mangan oxide electrode. So for this experiment, we actually were the contributors in the method development, but actually the scientific topic is coming from external users from UCL London, UK. So they asked for such kind of investigation. And the big challenge was to investigate actually the lithium distribution and the change of the cathode structure in this rolled structure, or this how to say, spiral shaped electrode. That's why we used virtual unrolling, and you can see here the electrode and the change of the contrast, which can be related to the change of the lithium concentration in the battery at different discharge states. So if you take a segment of the battery and unroll it, then we can see here what happens with the electrodes with X-rays and with neutrons. Actually, for X-rays, you see this dark area. This is the lithium, so we don't have any contrast for it. What we see is the mangan oxide electrode, and very clearly we can see actually the expansion of this mangan oxide electrode with the time. So you can see here that we have 6 discharge times or stages. In case of neutrons, we can see clearly the contrast for lithium, because the neutrons are very sensitive and absorb quite strong from the lithium. And you can see the diffusion of the lithium in the mangan oxide electrode. So this means the combination of the two kinds of radiation give us the full picture about the process in the battery. And in this case, actually, what we see here, we performed the measurement at the Conrad 2 instrument using 8 hours for tomography. So this high-resolution tomography took quite long time. That's why we performed some case study at ILL for how we can optimize actually the speed of the tomography. And for the next example, investigating Thionil lithium battery, we achieved about timestamp or time resolution of 7.5 minutes per tomography. And here you see actually this is not a 2D image, this is a slice of the battery from the tomography. So this is a three-dimensional view in the battery. And timely, you can see actually different process which happened in the battery. So you see how the electrode is, electrolyte level is changing. So this is this Thionil electrolyte, how we have diffusion of the metal lithium in the electrode. And of course, we can perform some quantitative study of the lithium consumption in the battery at different discharge times. So the combination of resolution and time resolution, or let's say speed, help us to investigate such systems in 3D. And get really very nice pictures, very nice picture about the processes which happen in such kind of energy-related systems like batteries. If we speak about other examples and interesting systems like fuel cells or hydrogen storage material, then the processes are much faster than this 7.5 minutes. So we need much faster response and methods for investigating of these systems. Therefore, we pushed the limits and we were able to investigate dynamic systems with much better time resolution. So here is an example of investigation of water uptake in plants from external users coming from the University of Potsdam. So here we used the contrast agent heavy water in order to see the water uptake. And as Alessandro mentioned, we achieved a resolution of 1.5 seconds for tomography. So the contrast agent helped us to investigate actually the activity of the roots in the sample, because uptaking heavy water, they lose contrast, and for this we can see the speed of the water uptake. So these are applications of using wide beam or the full spectrum of the neutrons. But for advanced imaging, in order to get access to diffraction contrast, for example, we need energy selective imaging. And here you see an example of weld between two steel plates at a wavelength of 4 angstrom. What we see here is actually the diffraction contrast. And for this, we used the monochromatic radiation, which was produced by double crystal monochromator, which give us chance to set a wavelength from 2 to about 6.5 angstrom. So here is one example where we can actually distinguish between martensitic and austenitic phases in trip steel, because for certain wavelength of 4.1 angstrom, we have different attenuation properties for the two different phases, and then we can resolve this tomographically in 3D for tension and torsion loading of these kind of samples. Actually, the diffraction gives a very nice agreement between the imaging contrast observed in this torsion and no, this is the tensile and the torsion sample, which give us the chance to say that neutron imaging can be really complementary method to diffraction in terms of observing of such kind of phase transitions. The grating interferometry help us to see the walls of the magnetic domains, and for this we use a coherent radiation, so we can just use such kind of line source where we have some transversal coherence length or transversal or spatial coherence of the radiation in one direction. And with phase grating, we can produce interferential pattern, which can be analyzed with analyzer grating. So for the first experiments, actually, our colleagues at PSI demonstrated that magnetic domain walls can be visualized by dark field contrast, where the amplitude of this interferential pattern is disturbed from the domain walls. And in this way, we can make visible actually the domain walls in iron silicon single crystal. Our contribution was to project this in 3D. So we performed dark field tomography at that time, and we were able to get the geometrical properties of the domains and confirm the theory where the domain width is actually dependent on the crystal thickness, and then we could contribute with few points to this theory. So using polarized neutrons for visualization of magnetic fields, we actually convert the precession angle of the spin of the neutrons to contrast. And here is how the contrast actually, the intensity is depending on the spin rotation. So finally, we could use polarimetric setup, and for different orientations of the spin, we can take tomography of the sample. So here is one example. So for orientation in X direction, we can take actually tomography of this small solenoid at X, Y, Z direction using flipper for the analyzer. And using all these 9 tomographies, because for X, Y, Z, we have 3 types of analyzers or analyzing the component, then it's possible to reconstruct the vector field. And this is a comparison between calculation, simulation, and measurement. So we have very good quantitative actually reconstruction of the vector field in this case. So here, as an example, the vector field in superconductor of first type superconductor of lead polycrystalline sample, where we had actually quantitative visualization of the field in there. So here we want to continue at ILL using the PhD program with our PhD student, joint PhD student, who started actually last year at HZB and performed the first experiments at the BER-2 reactor. And recently he performed already the first experiments at ILL. So we have great hope that this interesting method will be transferred actually without problems to ILL. So as a conclusion, the neutron instrument Conrad 2 served to a broad user community. So we are really very sad that we finished, but the good thing is that actually the know-how and the hardware will be transferred to ILL. And in the frame of this joint research unit, NIMATTERS, we can continue with our activities in the neutron imaging. So I would say bon voyage, NIMATTERS, and thank you for your attention. Thank you.
Thank you very much, Nikolai. You did a great job, like Alessandro and Lucas. So well done. So we've got a few questions here. Let me, a quick one. Did the heavy water kill the plant?
No, probably, let's say at BER-2 reactor, there was no problem. I don't expect also problem at ILL, because we performed also investigation in parallel using fluorescent activation analysis, where a fluorescent light was sent to the plant with wavelength where we have some reflection from the chlorophyll in the leaves of the plant, so we can monitor if the plant is producing chlorophyll during the investigation, and in this way we could see if the plant is feeling well or not. And we found out that over 2 days of investigations, exchanging water to heavy water and using neutrons, we had normal level of chlorophyll production in the leaves, and this was a good sign that the plants are okay.
Okay, I've always heard you can deuterate a dog and the dog will survive, so I guess a plant should be okay. But maybe that was a joke. A question from Frank Lee on polarized neutron imaging. Can you comment on how the depolarization from the sample would affect the results, and if there is an advantage or disadvantage of using time of flight neutron imaging, i.e. wavelength dependent imaging?
Yes, thank you for the nice question. So depolarization from the sample can be used actually as a feature, as effect, and not as defect, because if we are investigating, for example, phase transition from paramagnetic to ferromagnetic state, then we can catch exactly the point, the temperature of the phase transition, because in the ferromagnetic state we'll have full depolarization, which is not the case in the paramagnetic state. And in this case, we can perform such kind of investigations. This was done by our colleagues at FRM2, so they have very good experience on this. Using time of flight, actually, our colleagues from TU Copenhagen, DTU, together with Markus Strobel and the colleagues from PSI, performed experiments at JPark. So they succeeded also to reconstruct the tensor of the magnetic field, and this helps actually for better quantification, because using the time resolution, you can actually overtake the problem of the phase wrapping over, let's say, 2 pi, and this is actually the limitation of this quantitative magnetic imaging, because if we have rotation over 2 pi, then the contrast is no more unique, and it's difficult to reconstruct. So there is a paper about this which can be seen actually. Yeah.
Okay, I think we'll just have to take one more question in the interest of time. It's a pity there's lots of questions, and we've had great talks. So let's go for this one from Hasina from SNS, who says, great presentation, so thank you for that. For the martensite or austenite samples, how do you separate contrast due to the phase from the contrast due to texture using Bragg edge imaging?
So in the example what I have shown, it was not so quantitatively separation. It was done more or less on comparison between diffraction and imaging. But recently we performed tomography at different wavelengths, and then you can fit in every voxel of the volume with some function in order to get the position of the Bragg edge. And in this case, you have a 3D map of the positions of the Bragg edge positions, and then actually you can be more quantitative and get the real separation between the two phases. So this is something which is under publication, and I think that our colleagues at PSI have performed also such kind of study, if I'm not wrong, with performed at JPark as well. or at ISIS, I'm not quite sure, but they succeeded also to perform breakage tomography, let's say, and then be more quantitative in this case.
Okay, so thank you, Nikolai. So my applause to you.
Thank you very much.
On behalf of everybody. It's great that we've had so many questions. I can suggest that you, if you search for Next Grenoble in a browser, you find the website about the instrument and the project. And you can find more information there and contact details. And of course, there is also the ILL website where the instrument appears like all other ILL instruments, and you'll certainly find email addresses there. And you know the names of the people who've spoken, so I'm sure you can find email addresses easily using the internet these days. So I encourage all of you to look at this information and send emails to our speakers today if you've got further questions. So with that, a little bit over time, but I think we've got enough to be going on with. I'll hand over to Chino, who's got the challenging job of managing our directors and their directors' words in this event. So over to you, Chino.
Thank you, Mark. This is not a challenging job; it's a mission impossible. But I'll try to cope with it. So we have three talks that will be the three institutions or three people representing the three institutions who are jointly creating the what we are calling NIMAppers, and I will call them one after the other, reminding that they have, let's say, 5 to 10 minutes to say whatever they want. So we start with Helmut Schober, who is here representing the ILL. Please, Helmut.
Okay, thank you, Chino. So I'll try not to speak for 10 minutes, but we will see. So first, I think I would like to echo what so the speakers have said before me. It's really impressive to have so many people here for this event. And what impresses me most, I think some come from countries where it's about 6 in the morning. Others come from countries where it's midnight or later. So that imaging at ILL makes people get up early and stay late is really great. So I think that also for the whole team is a sure sign of the success they have created. I would like to go a little bit into history maybe, and it has already been said that ILL for a long time was not famous for looking favorably at imaging. The thing I think was that we said at the ILL, if we do imaging, we have to do it at the level of excellence, and we have to do it better than others. And the others we were confronted with, they were doing very well, as we have seen for example, from the Nikolai's talk in Berlin, but also the groups at PSI, FRM2 and LLB. So we wanted to wait for the moment where we were sure we could really compete at a good level. First attempts were done by Roland Geller, and I think I have to mention that here. But they did not materialize in a public instrument. So they were just tests showing that it works. It really took off, I think, when our industrial relations unit at the time with Jérôme Beaucourt, Thilo Pirling, Alexander Evans, when they looked into what could ILL do to set up a platform for industrial use at the ILL. And that was around the year 2010, so right after the financial crisis. They tried to bring money in via what was at the core at the time was called an EquiPack. And the imagen or the platform they wanted to build was Imagine. And this is also interesting how the names changed over the years. And what I think shows how sometimes science worked, and maybe without that we would not be here today, is that at the time there was a student, and that Jérôme told me this morning, Alexander Evans, And he had connections to 3SR and to Gino's predecessor, if I'm right, which was Jacques Derue, right, Gino. And so this way we had a letter already of intention at the time that 3SR would be interested in doing neutron imaging at the ILL. That did not fly. We didn't get we got good grades, but we didn't get the money. And so afterwards, we tried again with an instrument that was called APEX. And that, again, Jérôme pushed hard with many colleagues. Bob Cubitt was on board at the time. And this materialized in an instrument that was called D50. And D50 because Bill Sterling, as a director, didn't like instruments to be named anything other than D number, iron, a number. So that was the price to be paid. But this was a multi-purpose, and somehow at the time imaging was not on board, because one of the criticisms for APEX was it was too broad as a platform. So everything started first with reflectometry. But 3SR came back, and in 2016, as we have seen, they came back really with force, and they came back with money. They came back with a lot of enthusiasm, and they also had at the time an ally, I think, apart from Jérôme Bocquet, which was Charles Simon. I know that very well because it was Charles Simon who convinced the then science director, who was myself, that imaging after all could be a good idea at the ILL. And I repeated to Charles, I said, yes, I'm in favor if it becomes really excellent and we compete at the best level. And Charles said, with those people that we have now on board, that will materialize. So things developed, and it didn't take long that we had also the Berlin group on board. That was around 2018. And when I heard the names of Nikolai Kadylov and all his colleagues, in addition to the 3SR, I was really convinced that this thing will fly. And so it was introduced into endurance phase 2 at a rather late state, in an action where emails were circulated that we need a roadmap for this project within 2 days. So Charles Dewhurst, I exchanged with Gino, with Alessandro, and given their enthusiasm, no problem, within 2 days, there was a roadmap. And the roadmap said in 2020, there will be a public instrument at the ILL, right? And I think it's very rare that people write a roadmap and that in 2020 you can say everything they predicted so far has materialized. So again, excellent work, and we are really proud of you. So it's part of endurance, and I think the commitment of the ILL to this instrument shows up in two facts. It was part of endurance phase 2 when there was no green light from our associates. So we got just for next, which was at that time called Imagine 2020, right? It was not yet next. We got the green light to go ahead with this project because everybody thought it's a great thing to go forward. And then it's not frozen at the moment. All other endurance phase 2 projects are frozen. Next is the only one protected because it's we are engaged in this wonderful collaboration with our two partners. So we wanted to give some framework to that. And there is in France this possibility. I think it has not been mentioned, Unité Mixte Internationale, International Mixed Research Unit. And one of the real, I think, objectives of the direction of ILL was over the last 5 years to get really closely connected to the university here. So I'm really happy that this has happened. And I hope that it is something that will be an example for future collaborations, not only with French universities, maybe with other universities. And I would like to thank everybody involved in kicking that off. When I, for the first time, got the draft of what that could be, I thought, wow, this could be what we call in French an usine à gaz. So I said, no, please make it agile, make it lean, and make it efficient. And this is what they came up with. And in this context, a big thanks to our administrative departments, right? We often forget them, but the lawyers at the three institutions, they really exchanged very often, and they came to a common basis, and this across European countries, right? So not so easy. Great job, ladies and gentlemen, that you have done. And also a big thanks to the head of institutions, right? Jan is here with us. I think he will talk after me. But also Hervé. And at that point, I would like to mention Yacine Laknesh, because I think it was Yacine, when we needed this money in 2016, who said, yes, he was at the time responsible for the IRT. We go for it. And Yacine is now the president of the university. So you see, investing into imaging even is good for your career. So big thank you, and big thank you to the vice presidents for research at the UGA. I think the idea was growing at a dinner we had in the presence of Eric Saint-Amand, and Hervé has now picked that up. And again, a big thank you to Eric and Hervé for all the support we got from you. So now will provide, I think, an excellent framework. It assures a part of beam time for the two institutions that have invested so heavily into this. But it also brings this know-how. This know-how will come to profit to all our user programs. We will develop, as we have seen from Luca's talk, new techniques. Again, that will profit the whole field. And at this point, I know that Eberhard Lehmann is here. And Eberhard, for me, is a little bit the Mr. Imaging in Europe, right? And the whole community was always very supportive. I think this imaging field is really great in the sense that everybody wants to help everybody else. They never said, oh, a new competitor is coming up. To the contrary, they said, what advice can we give you? How can we help you? So a big thanks out to the community, and I hope, Eberhard, that after 20 years of frustration with the ILL, you finally have the feeling that we have done the right thing. So I will end like I have started. We have now an imaging that in its instrument that is at the highest standard and highly competitive. In the end, I feel like always this is a story of people. And what I must say, one of the greatest parts of this project is that I had the pleasure to be in contact with people, the enthusiasm of whom you just cannot beat, right? I just take Alessandro, also Gino, they're both Italians, so they have naturally a lot of energy by definition, by birth. But what they have put in place, the enthusiasm, the agility is impressive. And apart from that, all those people from HZB, from UGA, the ones internally, they were always a team. They always moved together. Really a great bunch of people. It's a great pleasure to have a beer with once this pandemic is over, right? I really can recommend you have a couple of beers with the next team. So in the name of the ILL, of the Neutron community, of all the great science you're gonna do on this instrument in the future, a big thank you to all those actors that right from the start, from Jérôme Beaucourt up to the end now with the new team, have made this possible, and a big thank you to the two institutions, UGA and HZB, who are our partner in this. So I don't know how long it took, but I hope not more than 10 minutes, Gino.
It took 12 minutes, but that was worth the time. Thank you very much, Helmut. I clearly see from enthusiasm that you might have some Italian origins yourself. Thank you very much. That was a clear and very nice talk. We go then directly to the second talk that is given by Jan Luning. He's representing the HZB. Please, Jan.
Hello, good afternoon, everybody, or good morning or good night. As Helmut pointed out, we are spanning the globe. I'm excited, and I think I'm also honored by being allowed to present the Helmholtz Center in Berlin here in this audience. I bring the greetings from my two colleagues with me. This has been truly exciting talks that showed the breadth of science that you can do with imaging. And as Nikolai just introduced in his talk, I mean, we have over the decades developed some expertise in this neutron imaging. And of course, we see this as a fantastic chance for us to transfer our knowledge, not only to transfer the instrumentation and knowledge, but also to continue to participate in neutron imaging activities together now with the two partners from the University of Grenoble and the ILL, the colleagues from there, as part of this NI Meta research unit. I have prepared a tiny little slides that I would like to share with you on this.
Please go ahead and share your screen, Jan.
Yeah, that did not work in the first try, but let me do it again. Here we are. As Nicola pointed out, and he said all about the history. Helmut all gave us the perspective where this goes. I just wanted to look back at these 15 years of history that we had in neutron imaging, and what really impressed me is that right from the start on, when this instrument took on operation, it was overbooked. So there was more demand that we actually could serve. And I think you see these growing numbers, and the fact that it flattens is only because frustration sets in. And of course, as it was said before, this community really needs more instruments, and it is exciting to see that the colleagues really don't see this as competition, but try to help each other to actually address this. And in this spirit, we're really excited that we can actually transfer also our knowledge to this new instrument at the ILL. This is not only that there's a big community, but it's also a community which is actually quite active and quite productive. We have seen examples of the exciting science that has come out, and we also see this, of course, in the numbers that even from our facility, we have a tremendous number of scientific results over the years. We had back 2 years ago, we had an evaluation of the scientific program of the Helmholtz Center in Berlin as part of the Helmholtz Society. And we actually got evaluated in 2 regards. The first one from operating the facility in the meta division. We see that this neutron instrument was really mentioned as one of the outstanding instruments and activities that we have. And then also from the more applied side, from using these instruments, also they acknowledge the excellent capabilities that this instrument actually provides, and really wrote it into our book that we should make sure that this stays available to the community beyond the lifetime of the BR2. So also in the name of the community that is actually behind these numbers of scientific output and the overbooking factors, actually we are very thankful that we have the ability to continue to provide the community with new imaging capabilities now at the ILL. Nikolai already showed you the scientific highlights, and I don't want to go, I don't even want to dare to say anything about them. I only want to mention or remind us that actually they went along with method development. And what really I like to see in the talk from Alessandro at one of his slides where he showed the instrument, he put all these labels that you see here, these illustrations along the beamline to illustrate where actually these developments that went along with producing these new scientific results actually will go into the next instrument and actually provide these capabilities to actually continue to do excellent science in all of these fields. And this is something which I like about imaging so much. It serves such a broad community. It has impact in so many fields. Being able to see things that you can't see otherwise, this is really something that stimulates our scientific thinking. Now, we actually very happy here at HZB that after shutting down the reactor, or in preparation for shutting down the reactor, we were actually able to find new homes for the instruments that we have developed over the decades at the facility. We already have transferred 6 instruments to other facilities. 10 are, so to speak, transferred as we talk because the contracts are signed. We are in the process of signing more contracts for the other 11 instruments. And we're even now in negotiation with a partner that actually could take over our large high field magnetic facility that we have just started to exploit over the coming years, that produced some fantastic results and really showed what you can do. Instrument development has been a big part of the BR facility, like it is also, of course, of the ILL and other facilities. So we're really happy that these instruments and all the knowledge that is in them actually will continue to serve the neutron science community. Now, I look forward to a productive collaboration. Let me just say, NI Matters, the joint research unit that we're going to form here together, it does matter to us. And we wish this joint research unit all the best. And we'll certainly do our part to make it flourish, to be productive. This is a project which is clearly driven by fascination, by scientific curiosity. And that's actually what makes the difference and makes things successful, whether you're Italian or not. So thank you very much for your attention. I wish the project all the best. I'm very thankful to all the colleagues that made it possible, that it's going to work. And I look forward to the fantastic scientific results that will be produced within this project. Thank you.
Thank you. Thank you very much, Jan. That was very, very clear, very kind, and very well said. So we come to the third and last presentation from the institution. That would be Hervé Courtois for UGA. Please, Hervé.
Thank you, Chino. Well, so I'm Hervé Courtois. I'm the Vice President for Research at the Université Grenoble Alpes since last January. In January, we had our new University Grenoble Alpes starting. Université Grenoble Alpes is now integrating all the higher education and research institution in the Grenoble area. So this is both from old university perspective, a few hundred years, and a very new university perspective that I'm happy to be here. At UGA, we have a lot of ambition. Ambition, I think, is always a good thing. An ambition, of course, is to be an inspiring place for our students. Also, we want to reach a high international visibility and to reach a scientific excellence. So we are on a good way, because this year we have been ranked in the top 100 in the Shanghai ranking. We'll see if we can maintain this, but at least this is a good sign. Of course, all this is possible thanks to our research institutes and laboratories that we run in collaboration with the national organisms, and also with the large-scale facilities that we had the great opportunity to have here in Grenoble. Coming back to NI Matters, so it is a long story. I did not follow that from the beginning, but I think that Helmut gave us a very nice history. I've been told this started in as early as 2015, precise discussions with Yassine Aknesh, who was at that time Vice President for Research, and Eric Saint-Amand took over this responsibility in 2016. So both Yassine and Eric really followed and supported very much this very nice project in collaboration with Bill Sterling at that time. So at ILL, UGA invested in terms of equipment, and we also created a chair for Alessandro Tangantini. This is quite rare. We do not create such a chair every year. This is something that we took very seriously, and we are very happy that Alessandro got this year associate professor position, a permanent position at the university at UGA in this with this project, within this very nice project, NI Matters. Of course, I need also to acknowledge the brilliant contribution of Cino Vigiani in this project. Well, he's a kind of leader you cannot say no to. this is a difficulty, but this is also a great chance, a great opportunity for us. This NI Matters is what you call the UME, as Helmut said, this international joint research unit with the University, Alpes, and HZB. We are very happy of this creation. It is also something that we need to celebrate. We do not have these kind of opportunities that often. We had some other projects, for example, with ESRF, but I think that this international research unit at ILL is the first that we have, and it's really a very nice example of what we can do here in Grenoble all together at mixing local research lab, international large-scale facilities, and the university. So I think I will stop here by saying that in the name of University Grenoble Alpes, I'm very happy and I congratulate all the partners in this very nice project and this new international research unit. And of course, I wish you the best for the future. Thank you.
Thank you so much, my vice president. I have the honor to close this meeting. We are a few minutes late, but not that much. Let me share my screen. Let's see if I can do it. This should work. Yeah. Do you see my screen?
Yes, we see.
Okay, so let me just show the 2-3 slides. The first one is, okay, that's a closure. When I give a presentation in journal, I introduce myself as being a professor at Université Grenoble Alpes and a researcher at 3ZR. That's why these two logos are here. Well, from today, I will need to add a third logo. That's the research unit NI Matters or NI Matters to which I will belong. It was said already by some of you, and I think this is very important. Ideas advance on finance. You need money to do stuff, but ideas advance on men's and women's legs above all. I think this is important. I think Helmut was mentioning that people matter. Not only Neutron, but also people matter quite a lot. And speaking of people, I must mention 3 persons who have been already mentioned: Jacques Deroux, Charles Simon, Jérôme Beaucourt. I remember more than 5 years ago, the first discussion with them and all the enthusiasm and the energy that they put into that. I should also mention on the institutional side, Yassine, Laknesh, Bill Sterling, and Helmut Schober. Of course, you need people, but you also need the support, an institutional support and some financial support. And I think that the support that we got from them was very strong. Although I should say at this point, I think that Helmut was mentioning that Bill was very much in favor of it. Helmut was not that convinced. So I'm very happy that a few years later, he said, okay, I think you were right, and now I'm with you. And then 2 key people here that I cannot avoid to mention, Alessandro Tengatini and Nikolai Kardilov. On the technical side, it's clear that what we have been discussing and what we will be doing for the next 5 years would just not be possible without them. Many other people should and could be mentioned, but then that would take me another couple of hours, and I think we are almost to the end. So let's go to again, people. This is an historical picture. That's December 2015. We are at the ILL. These comes from a previous era in which humans would meet each other without masks and they would even drink together. Remember that era? Must be something well, it happened. It used to happen. I hope it will happen again. We were signing an agreement between ILL and what it was still called in 2015, Université Joseph Fourier. It became UGA a few weeks later. A few days later, in fact. Well, Bill was drinking, was signing, And then there is this picture that I found on my computer, and I like it very much because you see, well, the three of us are younger, that's clear. Helmut is quite happy. Yassine is very happy. And you see that I'm not that happy. I look worried in this picture. I'm not smiling as much as the two are. And the reason why is that we were starting a big adventure. I was not quite sure about the success of it. Now, 5 years later, we are signing in a formal way an agreement on the creation and operation of a joint research unit that we decided to call Neutron Imaging for the Mechanics of Materials and Energy Research. And I think the three keywords are important: mechanics, materials, energy. And that's why we came out with these NI matters. Now, I should also stress the fact that as an integral part of this agreement, there is the creation of a shared imaging for mechanics, and Hervé reminded to everybody that this is not a usual thing, it's a special thing. There is a shareholder that is Alessandro Tengatini. And I would say just 2 words about the governance. So the unit will be governed by a steering committee, and this steering committee includes 3 people, 1 from UGA, 1 from HZB, and 1 from ILL. There is also a support by an international scientific committee. And here in red, you see the word external. This has been the case from the very beginning. If we do that, is to let's say, to carry out and to do good science. And we all know that the only reason to do good science is to ask for the comments and criticism and review by the peers. This is not an internal game. We like to have an external committee that will be guide and help us to do good science. I will not go into the details of the scientific goal. I just want to say that there is a number of them. We want to broaden the range of process. We want expand the accessible scales in terms of space and time, but also, as Nikolai was mentioning, mechanisms. We want to provide data set that can inform and develop modeling. Modeling is part of the game. And finally, we would like to enrich the user program based on this development. I think it's important to close because we are late. I want to show this. I couldn't resist to the temptation of showing this piece of paper in which you can see the signatures of all the 3 institutions. So it exists. It's official. It's official since September 1st. And the agreement says that this unit has been creating for the next coming 5 years. So what's the future? Because we show picture from the past, but what about the future? I would say that the future for now is 2020 all the way to 2024. And why not beyond? Today, I must tell you that I feel very happy, that I feel very proud, and I'm positive. Then I realized that these days is not a good thing to say that I'm positive. So I'm optimistic. Positive is not a word to be used these days. It can be misinterpreted. So my final message is the following. We all agreed that although today it had to be just a virtual event, which is a pity, although it's very nice to have all these people attending it, well, we still hope that in 1 year from now, we will have a scientific event with many presentations by scientists that have been working with us or in the unit. And we hope to see you all, hopefully in person, in 1 year from now for celebrating and assessing what we would be able to do in the next. I think that with these words, I would like to close the event. I think it was extremely successful. I think it was extremely impressive to see that more than 200 people were there. Well, now they're a bit less than, now I see that we are 133, but we're the peak of 208. So these are good numbers. As it was said, they are good numbers for the imaging community, not only in Grenoble. And I think there are good numbers for the 3 institutions who decided to invest on it. I think that they did a good job on it. And I am sure that they will continue to support us, not only financially, but support us as a project. I think that budget is important, but I think that having the support of our institution is not less important. In this respect, I think that many people who are here today know who I'm talking about. So thank you very much. Thank you all. This has been recorded, so this will be made available to the community. Perhaps my colleagues at ILL will tell you more about how does it work, where you can download it. But it was a great pleasure, a great honor having you here. So I declare officially, and I hope that the three directors will not say you are wrong, I declare officially that the unit NI matters does exist. Thank you very much and have a good time.
Thank you, Gino.
Thank you, Chino.
Thank you, Chino.
Thank you and goodbye.
Thank you. Thank you very much. Goodbye.
very much.
Bye-bye, everyone.
Goodbye.
Have a good weekend. Bye-bye.